Getting started. Almost there. Oh, there's a lot of tabs. To see all that. That one. Okay. Recording has started. G'day everybody. Thank you for joining me. Those who are joining me live. Thank you for joining me after the fact. For those who are joining me not live, watching me on Echo 360 later. Hopefully it's not the day before the exam, because maybe that would be too late to, to learn some of this material. Not too late, but it's never too late to learn things. But hopefully you're watching this well before the end of week 12, and if you're watching it after week 12, it's the second time you've watched it. So that's all I'll say about that. Just making sure that all my stuff is looking good. I think I can see myself. There I am. I made myself a bit bigger in the slide now. Just I thought like there wasn't enough of me. I'd like to be more of the star of the show here in the Charles Lab. What are we talking about today? We've got our big 2-hour lecture. We're going to talk about functions. Hopefully we go for something like 2 hours. I might have to stop a bit before that. I've had a bit of a cold and my voice will run out before I get to 2 hours, I think. So we'll see how we get to, but it might be before that much time goes by. But we'll definitely learn a lot about functions, and we'll definitely do some great examples. I will say one thing here to start with. Functions are incredibly important in COMP2300. Incredibly important. And you haven't done them yet. So it's very important to pay attention to this lecture. The other thing I'll say is they're not as hard as you might think. Compared with last week's work, where we had these really fiddly conditional branching arrangements, functions are way easier. In fact, it's a relief when you know how to do them, because it means that you can write your code properly and you feel like you've got some structure in the world. So thank goodness we get to do functions this week. The Charles Show. Yeah, it should be. Is that a clip from my what's that other thing? Twitch. Yeah, I'm a Twitch something, affiliate or a something. Anyway, you join my Twitch so I get to be more of the things. I can have the Charles Show all day, every day, forever. Before we get into the content, I'm going to show you something. It is this week's lab. This is lab 5. Warning at the top of lab 5. This lab includes in-lab assessment for assignment 1 pre-submission task. Read about that, how that works on the assignment pre-submission page. I'll go to the assignment pre-submission page. If you haven't seen this page yet, well, this should not be the first time you're seeing this page, but if it is, go to it right now. Here is the URL. It's very small, but you can find it yourself on the assessments page of the COMP2300 website. What do you need to do for this task? You need to do 2 things, or 3 things. Fork and clone the assignment template repository. You'll find that on the assignment page. That's thing 1. 2, write a design proposal, 200 words or fewer, that outlines what your planned design is and how you will accomplish it. 3, the third thing is go to your lab and talk about it with your tutor. That's the whole assignment pre-submission task. The whole point of this is to get you to have an idea, write it down. Even if you don't quite know how it's going to work yet, that's fine. Even if you think, I don't have enough information, just write something down to the best information that you've got right now, this week. Write it down so you can have a conversation with your tutor about how you're going to do the assignment. All of this prep work, cloning, forking, writing the design proposal, it all leads towards a very important conversation. But you can't have that conversation unless you've done the necessary thinking beforehand to write down an idea and have that reflection. I'll point out a few things. You are putting this, where's the assignment template? There it is. You'll fork and clone this fork. I can see 195 forks. I should be seeing 400 forks. There are 400 students in the class. What are you all doing? Go do it right now. Fork it. Fork the assignment. Design proposal. Once you've forked it, in your fork of the assignment, you will write in design proposal some stuff. If I just look at the raw version of this, I mean, you could even do it in the IDE on you don't even have to clone it, just fork it and write it in the IDE. You delete this bit, and then you write, my assignment is going to do something great. You need to write more than that, right? I'm looking for something roughly 100 to 200 words to be a serious attempt at this task. I will note a few things. The deadline for this is due by the start of your week 5 lab. You are all registered in a lab in this course. The lab you are registered in is the deadline for this task. At the start of your lab, your tutor will run a command which will harvest your design proposals from your GitLab repositories. If your design proposal is not in that GitLab repository, or your GitLab repository hasn't been forked, you don't get a mark for this assessment. So the deadline is including all of those stages: forking and cloning the repository, filling in the design proposal, typing it in here, saying commit changes. It'll be there in GitLab for your tutor to get it. I'm not going to commit it into the template. That would be bad. No, 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 no. Leave page. Bye-bye. Okay, you don't commit it into the template. Commit it into your own fork. If you haven't done this by the start of the lab, you won't get a mark for this. It needs to be done there. You can certainly have a conversation with your tutor, but it won't be a very good one because you haven't thought about what your assignment's going to be. It's not a big mark here, 1 mark per assignment. It's 1 mark out of the whole course of 100 marks. Most students will get the mark if you've made a serious attempt at this. Length, 200 words or fewer. 200 words or fewer, not 200 words or more. I was having a look at some people's assignment submissions, pre-submissions, their assignment design proposals this morning, and I was seeing some from very good students which looked like very good proposals that were more than 200 words. 200 words or fewer is the specification for this task. In this task, if you go above the word limit by a significant amount, you can expect not to get a great mark. Someone said they didn't check their word count. It would be a good idea to check it. That person who's saying that they ought to check their word count, I would suggest very strongly that they go to check their word count right now, because I've seen their design proposal and it's more than 200 words. So I think you can probably check word count right in VS Code. Word count, probably not in what about a markdown document? You can do all kinds of markdown stuff in VS Code. Markdown preview. Ooh, markdown, open preview to the side. There's my markdown preview. I'll make it all a bit bigger. Word count. I don't know, there's probably a word count. It's probably a word count extension you can install, but there's not any good ones right there. Look, just figure out how to do a word count, all right, folks? You're grown-ups, you can count the words in an assignment submission. You know, I'm not going to be taking off marks for the 201th word, but if you're like way more than a normal kind of margin of error is 10%, if you're more than 10% over the word limit, expect that is not going to be getting a full consideration from your tutor. Doesn't matter if the pipeline fails. No, it doesn't matter if the pipeline fails. The pipeline for your assignment should fail until you do the assignment, in which case it will work. What's the pipelines? What pipelines have we got here? Oh, yeah, there's a few different pipelines. I remember now. We'll talk about this more maybe next week. There are 3 pipelines for your assignment. You should get, this one should work. When your proposal is more than 25 words, this pipeline passes. oops. You've got another one which is your statement of originality. Once you've filled in your statement of originality for your assignment, after you've completed your assignment, this pipeline will pass. And then the final one is this one. When you've filled in your design document, which should be more than 50 words, this pipeline will pass. And that actually means that your design document will be deployed. It will create an HTML file from your design document, which is pretty cool. Cool stuff. And this one will always run. It just shows that your assignment builds. The template assignment builds already. Any other questions about the design proposal right now? Read this carefully. If you show up to your lab without completing your process for your design proposal, you will get 0 for that mark. Some of my tutors are chatting to me in the general channel for the tutor team, so I keep getting these pings. You don't have to go into great detail here. It's roughly what you want to build and roughly how you will accomplish it in ARM v7. It's just to give your tutor and you something to talk about. So it's a proposal of an idea for what your assignment's going to be. Obviously, this assignment has many possibilities. And just from the top of your head, what you're going to do to make that happen. It shouldn't need to be more than 200 words, but to make it significant, it should be between 100 and 200. Just talking about the assignment again, the assignment also has a writing task, and I'll note that there is also a word limit here. Your design document in your assignment must be maximum 600 words. We actually have a resources page about writing a great design document, which is, I encourage everyone to read. Everyone in the class, please read this one. Maximum 600 words, talks about how to write in Markdown, has a lot of hints of how to structure a design document and make it look really good. I might just show you my, it's a fake design document. I will just try to find it here. I'm not going to show you any exam questions or anything. That's for a different course, luckily. COMP2300, 2022. Assignment 1 is a bit dangerous showing the students your private repositories on GitLab because it could have all kinds of important information. This is my fork of the assignment repository. I was just forked it to test how things would work. Have I got a design proposal? Yeah, it's got some lorem ipsum, some sample text in there. I've made sure that my design proposal is text. It's not in a HTML comment, so it's showing up when I look at the screen here. Your tutor will ask you to bring up your assignment repository on your screen in your lab to show this text here so they can see what you've done. I'll just show you that I've also written a sample design document or taken some text out of a different file, different Markdown file. You see, you can use images within Markdown in your design document. It'll all show up really nicely if you do that. So please look at that design document page and learn about how to write a nice Markdown file. Okay, on with the topics for today. Functions. If there's any questions about your assignment pre-submission, please ask them on Piazza today, because the first people's ones are due first thing tomorrow morning, Tuesday, 8 a.m. lab. Finally, functions. You must have been waiting for this chance, particularly because you've all studied Haskell in COMP2300 or the like similar courses. So you will be thinking, why can't I use functions? That was so important in first year. Now I'm in second year, we haven't done any at all. Well, now we get to know how to do it. But of course we needed to learn a lot of things to get up to this point because assembly is working from first principles and how your computer works. So now you've learned about branching, you've learned about conditional branching, and you've learned about memory already, and we're going to start to combine these concepts into how to make a function that does what we would expect it to do. So why do we need functions? Because it sucks to copy-paste code all the time. And I've seen some folks starting to do more copy-pasting than you'd want in their LED blinking lab when people have started to copy paste little delay routines or something, because it's just a total pain to have to branch in and out of things without being able to branch back reliably. We don't quite know how to do that. You can branch to a different bit of code, but it's hard to get back to where you started. So copy pasting sucks. That's why we need functions. Let's have a look at some functions. Here we get 3 functions in different programming languages. Def +1 of x, return x plus 1, a classic function in Python. Then the same function in Java. Public string +1, int x, return x plus 1. Why is it returning a string? That doesn't make any sense. Oh well. It's a broken Java function. It seems like it would return an int rather than a string. Then we got a function, I guess in Scheme, at the bottom, a functional language, plus x1, lambda x, define +1, another way of defining a function. What do all of these functions have? They've all got, wrong color, they've all got an argument, or a parameter, I guess you could say, parameter, and they all have a return value. But are these things necessary for a function? Some functions have arguments and return values. But I say these functions don't come pre-made. That's right, in assembly there is some assembly required. These functions happen to have arguments and return values, but you don't have to have those in a function. You can easily write this function, something, in Python. It's fine. Def something, does nothing, and then there's no return value. It just drops off the end. That's a totally valid function in Python. You don't need to have return values and you don't need to have arguments. Really, a function is just kind of a little capsule of code that you can use over and over again. And the return value and the argument are just an extra part of it that we need sometimes. Often it's very useful, but we don't need it all the time. So let's look at some function analogies. Here's a decent analogy, a good analogy, some kind of pipes with input and output. So these pipes are getting some numbers in, they're getting x's in at this side, and they're spitting out x plus 1s at the other side. That's a good analogy, but you know, I said a minute ago that functions didn't need to have inputs and outputs. So if we're writing a function that doesn't have an input or an output, this analogy doesn't make much sense. Here's a better analogy, there and back again. So you can think of our function as kind of like a journey to go somewhere else and then come back where we started. And you might recall a series of movies or a series of books about some people that live in little hills in the ground. And one of these little ground hill people goes on a journey to do some stuff, and along the way meets some giants, and they make them stay up all night, they turn to stone. Along the way lands in a forest where there's some spiders, and gets in trouble with them, goes over some big mountains where there's some big battles and all kinds of stuff going on, ends up behind the mountains meeting some, I don't know, some other different folks who live behind the mountains in the forest, who live some folks on a lake, and they live in sort of houses on stilts, and then goes and battles with a great dragon. Is this the worst dragon you've ever seen? Probably. How many legs does a dragon have? Do they have 4 legs or 2 legs? Because they've also got wingerlings. Okay. The dragon gets arrowed. Blah. And then what happens then? Our heroes come all the way back down. They visit the last place they were. They visit the last place they were. Visit the last place they were. And come back revisiting all of these places that they've been. Back home again. Someone's asking, is this Shrek? No, it's not Shrek. I don't know what Shrek is. I do know what Shrek is. I should just claim I have nothing to do with J.R.R. Tolkien's estate. This is about neutral, generic, abstract class of hill-dwelling people, hill-dwellers. Not anything licensed by any particular person. But, you know, this sort of story follows what we could do from in many kind of adventure games in the realm of fantasy and science fiction. There are many stories like this, a hero's adventure where someone goes on an adventure, they have many things along the way, and they have sub-adventures, go and do something and then return to the main adventure, return to the main adventure, return to the main adventure after that. And then they're on this bigger main adventure, which then lets them return to where they started with. And we can think of this like our program and like functions, because the function is some line of code over here. And we're going to go all the way over to there, start this section of code, which lives somewhere else. This is our main program down here, just living a quiet hill-dwelling life, farming potatoes or whatever they would do with their hills. Whoops, we have to go on an adventure. Adventure time is written in there. Go to this function, do this. They go on this big adventure, run this code, and then at the end of the adventure, they go all the way back home. They're a happy potato farmer again, and they continue on with their program. So there and back again. We're going over there to some different code, and we come all the way back. While we're on our big adventure, we might have other sub-adventures. These are all sub-adventures where we start this line of code there, and at the end of it, we go back again. So you can have functions and sub-functions within those functions, nested functions. You can have functions that run and then another function runs. Someone's giving the game away in the chat of all the things we have to do. Anyway, so you get what I mean, right? There's this idea of doing your normal life, that's your normal program, and then a function is going and doing some different activities that are completely different from what you were doing and coming back to there. I guess this analogy doesn't cope with the idea of things being reusable, because it's not like there are a whole sequence of hill dwellers going and doing this dragon adventure. But if we were in a massive multiplayer open world RPG, maybe there would be, because everybody on the internet would want to go and play the same game and do the same adventure. So this adventure script, adventure function is available for everybody. Okay, enough adventures. Here's another analogy, one that you might be very familiar with from studying maths or from high school. Functions that deal with numbers. So this is strictly an in-out analogy, isn't it? The maths version, the maths kind of function, where we have some input values, we do some calculation and we get an output. So again, this is similar to the pipe in and out. It does have some good ways of describing how functions work in computing, but it's not covering the whole thing. It's not covering the there and back again aspect. So here's a function call in our program. This is our regular life going forward. Different lines of code are running. At some point, a function call happens. We call the function. Hello, function. Go on an adventure. Pursue your dreams. Go into the function adventure and run that line of code, and then go all the way back to exactly where we left off in our code, the very next line. And down here, it might happen again. The same function might run. It might go have a venture up down there, run the same code, and come back. So it's a reusable block of code. So the question here is, can we do this with branch? I know it sounds a lot like branching, and it is branching, but there are some key differences that we need to keep track of as assembly programmers. Someone says it does sound like branching. Absolutely. Can we do this with branch? Well, we can certainly do this bit, but what about this bit? And that's where I think people get stuck with branch. Because you can branch to a label. Suppose we call that label. we can branch to here, that label, and then when we get to the end, we want to go exactly where we left off. So I guess in our code, we could have label 2 there. We could branch back to label 2, B label 2. But then what about the second time we want to use this function? We could B label down there. And then when we get to label 2, we're not going to go down here. We're going to end up back in the same spot again, which is not what we wanted. So it's not going to work with just B, the branch command. It doesn't work with just B. So there's an extra part of this that somehow when we branch to our function, we need to take a bit of information with us about where we came from. It's like if the hill dwellers went off to fight the dragon and then they didn't know which hills they lived under when they got back. They wouldn't know whether they were hill dwellers or whether they were forest people or whether they were fish dudes or whether they were mountain creatures or, I don't know, slime trolls. There could be all these different creatures could be having a dragon adventure but they can't remember where they have to go back to. And the branch instruction doesn't let us keep a memory of where we were when we started. So we have to do something a bit more. So here's our open questions that we're going to talk about this week. How does the program know where to go back to? How do we pass information, that is parameters, into the function? How do we get information, that is return values, back out? And can we have some scribble paper while we're on our adventure in the function? Our 4 important questions. So it's a bit more than just branching, isn't it? There's all this other business to do with other aspects of what a function is. So parameters, arguments, different words for the same thing there. Now, we'll go with another small analogy or a reminder of a fairy tale called Hansel and Gretel. Hansel and Gretel. What did Hansel and Gretel do? Well, they went on an adventure away from their parents to a gingerbread house and got caught by a witch, and then they tried to make their way home again. How did they make their way home? Well, they tried to leave a trail of breadcrumbs behind them so they could find their way back. So they tried to have some way of storing the way back to where they'd started so they can find their way home. Not sure that I actually told an accurate version of Hansel and Gretel. I know it involves breadcrumbs, a witch, trying to go home again, and some children, but I've forgotten the rest of it. So feel free to fill me in. I'm not sure if I'm going to come into any copyright issues with Hansel and Gretel. So here's the big reveal. These two friends, BL and BX, 2 different instructions, which do appear, I believe, on your cheat sheet. Branches. So you might have seen them already. What does BL do and what does BX do? So B, the regular branch command instruction, always has to go to a label. BL is happy to go to a label, just the same, but it's going to do another thing. This is the same as branch, the regular branch instruction. The L stands for link. It's branch and link. And the link bit means that it stores where it was up to in the program. The value of the program counter is stored in this register called LR. And LR actually stands for link register. BL, branch with link. So when the branch with link instruction is executed, the address of the next instruction, that is the one after the BL instruction, is placed in a specific register, and that register is called LR, the link register. I'll just go through that again. When the branch and link instruction is executed, BL, the address of the next instruction just after the BL instruction is placed into LR. So it's one of these special registers. bx, this is another really important one. So we've got this value now in the link register, a program counter value, which is going to lead us back to our program. How do we get back to there? We can't use the regular B instruction because that only works with labels. What we need to do is to use this branch with link, or I mean, the regular branch instruction works with immediate values. The label is an immediate value. It's the same thing. But we can't know what that immediate value was when we're running our program because this function might have been run multiple times. So we need to get that value from a register, and the only branch instruction which is allowed to go with a register is bx or blx, but we're only going to talk about bx. That's the only one we really need. So that changes PC to be the value stored in rm, bx rm. So the bx instruction branches not to a static label, that is a memory address. I think my screen's a bit too big. I have to do a bit of experimentation with my zoom on my screen. Memory address. But to an address in a register, that is usually LR. So what you will see is often this line of code, bx LR. We're returning branch back to whatever address is stored in the link register. So bx, it's the name of that function is branch and exchange. That's why it has an x. We don't have to worry about the exchange part very much. It's there for an important reason, but not a reason that's useful for us. This is to do with the ARM ISA and the fact that ARM chips like the Cortex-M4 support different modes. You can often switch between ARM and thumb execution modes. Actually, I don't know if the Cortex-M4 does support ARM execution, but some do. We only ever use thumb in this course, but BX might allow you to have one program that has some bits written in ARM ISA and some bits written in the thumb ISA. You can read more information on that slide about how that works, but it's not something we need to worry too much about. How do we put this together? Here's our little program. A bunch of stuff happens. Then we run BL +1 to go to a register. We do something in this register, in this function, I mean. We run BL +1 to go to a function, not to go to a register. The function is called +1, and it has this label called +1. Here's the body of the function, add R0 and 1, and then BXLR, and it just takes us back. And that takes us back to this instruction that we can run now, that one. So this is this +1 function correctly written in assembly. Okay, no one's got any questions so far, so I presume everything is super great, but I'll pause in a minute and see if anyone has a question for me. One question you might be asking yourself is, does BL work with conditional branches? As it turns out, it doesn't. The regular B supports conditional branches, but BL doesn't. You can use IT blocks to get around this, or you could use a regular standard conditional branch to branch to a place where you're going to then branch to a function. But so there's a couple of ways to get around that. I would suggest getting used to IT blocks if you wanted to do something important. Yeah, someone has just corrected me, and it's true. Cortex-M processors don't support 32-bit ARM instructions or the standard ARM ISA. We always use the modern ARM ISA, which is called Thumb, or Thumb 2, I think is actually what we use. So we still have this legacy of knowledge about the execution modes, but it's not useful in our processor. Someone's asked, so we need to use BL to have a BX in the function. You don't need to, but it's very convenient to. If I had some code, start writing a function now. We'll delete all this stuff from last week. Okay, I've got my regular main loop here. And I'm going to make a function. You know, mov. I can certainly branch to this function. B. This will work, but if I use just regular B, my LR isn't going to contain the right value. So you could probably do something like mov LR, you know, like, I'm making this up here, PC plus 4 or something, and then use branch. But why would you do that if you if you didn't want to do this? If you wanted to use LR at the end of BXLR at the end of a function, why would you go through this weird stuff? There are some reasons you might want to manually. Actually, I don't think you can mov into LR. You'd have to use the special commands to change those special registers. But why would you need to do this? You'd have to be doing something weird. So right now we're not doing anything weird. We're only doing normal things, and if we want to move to a function, you should always use BL test function. This sets up LR correctly. Woohoo, everyone's happy. So here's a template for what a function might look like. A function starts with a normal label, and it has some stuff in the body of the function, and then it ends with BXLR. I'll say it again. This is what a function looks like. And if I ask you to write a function in an exam, you should always start with a label and end with a BXLR, because they are what makes a function a function. It's a place to go, and it's a way to get back. That's the absolute main stuff about a function. There's another question, I'll answer that in a second. The most important thing about a function is the there and back again aspect. The label is how we get there, and the BXLR is how we go back. There's this other stuff, dot type, then a function, the name of the function, that's the same as this part, and the percent function bit. This is only for the benefit of the assembler. And it lets us do things like the function disassembly, or helps with that. You don't need it. It doesn't need to be there for a function to be a function. What defines a function is there, that is the label, and the back again, BXLR. Everything else is optional. So it's a really simple concept, really, just there and back again in our code. Now, someone asked me a question, which was, can I set LR to be something outside of the code region? Can that point to some data? No, you can set LR to be whatever you want. There's a way to change LR, but if you're running in regular RAM that's not marked as executable, your program won't be able to run. So some of the RAM is marked as data. Your code memory is marked as read-only. It's also marked as executable. I think the other regular bits of RAM aren't executable in general, but they can be changed to be executable, I think, somehow. Sure, you can run, obviously we can run programs in RAM. Mostly when you run a program on your computer, the whole of the program is copied into RAM, and then your CPU runs it bit by bit. So you can use BXLR to run things out of the code part of memory. You just have to do what needs to be done to make that work. It's a bit this discussion about different bits of memory, which bits can run, which bits can't, how you might change that, is a bit of a topic for the operating systems part of 2300, so we'll get to that in a few weeks. But great question. We can certainly change LR to point anywhere we want, and it might be useful to do that. So I guess BXLR isn't only used for functions. Most likely we use it in functions, but it could be used for other stuff. Functions are simple. You start with a BL label to branch to it. That's how you get to the function. You use a BXLR instruction to come back. I cannot express to you how simple this is. It's really just those two things. But we haven't talked about them so far, so they're important to go over now. And I think we went through this analogy, the RPG quests. Now we get to this point. And I think going back to our analogy, I discussed how we might start with the hill-dwelling person, and they are going on their adventure, and there's a big dragon at the end. This is going to be a worse dragon than last time. Does anyone know about the video called Trogdor from back in the day? Trogdor was a man, but he was a dragon. Anyway, look it up if you don't know. Classic stuff. Classic millennial memes. You might want to go to battle the dragon, but along the way we have these other things that happen. We meet the giants. I don't know why that's a giant. Oh, it looks sort of giant. We meet the giants and we have a sub-adventure. So there's kind of a function within a function. That's a function going on. And this is a function. Along the way to this function, we start another one. And of course you want to do that. You want to run a function, then get into another function. And then maybe inside that function, have another function. It's functions all the way down. We can do this. But we need to look after a few things. Because when we said BL adventure, we set LR to be hill. Okay, I'm making an analogy here. So that implies LR equals hill. And then maybe we got to the forest. That's a forest of trees. And now we're setting LR to be forest. And then we do the giant adventure and we keep going to the dragon and we come back. And when we return, we're actually going back to forest. We're branching BX to forest instead of back to the hill. So our adventuring has been broken. This happens all the time when you're playing like an adventure game. Someone said Elder Scrolls, right? When I'm playing Skyrim, I always get distracted by subquests. I never finish the original subquest I was on. So we don't want to get distracted by subquests here. We want to be able to run our function, go to another function, come back there to where we were doing something, run another function, be able to come back there, and then right at the end of the function when we have BXLR, we want to go all the way back into our program. This is where things get interesting. We need to do a little bit more work with functions than just a label in BXLR if we want to have a feature like nested functions. So I guess we go back to our other analogy, the Hansel and Gretel analogy. In the case of Hansel and Gretel, they used breadcrumbs, but they all disappeared. Birds ate them or something, so they couldn't go home. And then the witch ate them, so that was the end of Hansel and Gretel. So don't just use breadcrumbs. You have to be a bit more conscientious about finding your way home than Hansel and Gretel were in the story. Here's another example of it being broken. Broken stuff. Looks a bit dodgy just to have these bits of slides cut out, but Uwe went to a lot of work to make these PDFs, so I'm very happy to keep using them. Maybe one day I'll change them. BL plus 2. Oh, what? I don't know. I've forgotten Hansel and Gretel, but if the breadcrumbs got eaten, how did they... Someone says that they threw the witch in the oven. I thought the witch ate them. I don't know. The witch would certainly eat them if they don't look after their link register. BL plus 2 is going to set link register to point to that. So link register is just one thing in the world. It's a static, a global variable essentially. It's a register which is always going to exist. We only have one link register. Now when we run BL plus 1, our link register is going to be pointing to that line of code. And this one is gotten erased. Then when we run this second BL plus 1, the link register is going to point to this one. So when we do BXLR, our code is not going to return back to here, it's going to return back to here, because that's where LR points to. So we're going to have to some way save our LR, keep it safe, keep it secret, keep it safe. Not quoting any particular hill-dwelling mysteries, adventure stories. Store our LR somewhere. We've got to stop the first return address getting clobbered. So how are we going to do that? You folks tell me. How are we going to stop this LR getting clobbered? What are we going to do? There's already been some discussion on Piazza about it, actually. And I just want to say at this moment, while you're composing your replies, how happy I am to see so much Piazza activity. People are really asking some great questions, coming up with great answers, and I hope to see more of it when we're getting towards our assignment, because people will come into problems. Hopefully you can ask your questions in a way that is not showing off your assignment solution, but asking for genuine help from other people, and you get it. So do use the Piazza forum. It's great to see. What can we do with our first return address? Someone said store it in a register. Well, we already stored it in a register before. I guess the problem is that we're going to, if we only have 12 registers that are useful for this, so we could move it into another one. But then if we ran, suppose plus 1 had like, it could be mov LR, or backwards, sorry, mov R2 LR. We'll say we'll store LR in R2, and then at the end of it we restore whatever was in LR. I don't know, or we get mov LR R2 there or something. But oh, if every one of these functions, I suppose, used R2 to store the link register, this one would still clobber it. So that's, sorry, I have explained myself poorly, but what I mean is, at the start of our function, we could store LR in R2, for instance, but then some other function might just write over it again. So it's not going to be a long-term solution. So someone says store it in memory, which is great. Where are we going to store it? If only we had some kind of special storage place that functions could use to store things. And actually we do. We have a special storage place for functions to store things, which is called the stack. Stack. And this stack is the final piece of the puzzle to do with functions. And I'm going to spend most of the rest of the slides, you see this bar, explaining stuff to do with the stack. This is the thing which is a little bit more complicated, I guess, than just the basic label BXLR part of a function. So here we go. We've got this label SP. It's another special register. It doesn't stand for special, it stands for stack pointer. Stack pointer. So at the start of our function, we store LR at the location of the stack pointer, and at the end we load LR, load the location of the stack pointer into LR, and we get to go back where we started. Someone said says on this slide there's an issue with SP, which I guess there could be an issue with SP. I'm not sure exactly what it is. I can think of an issue which you maybe is only slight. It's really just like we're not quite using it properly in this instance, but it could work. This could work. Should we try it? Let's make some functions here. I'll do the demo +1. Oops. Hope my head's not over it. So just first of all, just a regular single old function. BL, well, we'll start with B, plus 1, mov R0, 0. Oh, plus 1 has to add, really, doesn't it? Add R0, 1. Let's try this one on a microbit. So I'm just using regular old B here, just to see what happens. So there's something in our link register. Mov R0, 0. So far, so good. Go to the plus 1. Add 1 to R0. We got 1 in R0, and then we BXLR, and we end up somewhere in our startup.s because the last thing that happened was BL main. Actually, main is a function. This whole thing is a function which has been called from startup.s. So sorry, someone asked made a good point there, which was why the SP thing is wrong and it's got distracted. The last thing that happened in the program was BL to main, so the link register is set up to return to this location, which is the end of the program. So there's nothing else to do there. So we need to use BL, and then we should be able to see the correct behavior. Move 0 into R0, BL plus 1, adding 1 to it, BXLR come back, loop again, does the same thing. Now you might see that we now can use our step over button here. This lets us, if we don't want to go inside a function, we can use step over just to jump straight over the top. So it runs all the stuff in the function and just goes straight to the next line of code. So if you end up using a lot of functions in your code, which you should be, using the step over button in the debugger is useful. Okay. So now we'll do our function within a function. Plus 2. And from memory, plus 2 went like this. BL plus 1. BL plus 1. What? PL? No, BL. I'm putting a few nops in here just so it's clear what's going on. So I've now got functions within functions. I start with 0. I want to use plus 2. And I just use the plus 1 function twice. This should work, right? Let's find out. I go inside plus 2. LR is set to OX20B. Go inside plus 1. Do that. LR, so far so good. Go inside BL, go in that, add 1 again, now it's 2, return, we got a NOP, BLXR, and we end up stuck here, because our LR was pointing to that NOP. Now what was it we were supposed to be doing in the... Oh, there's too many conversations going on at once over on my other computer that I'm involved with. Storing and loading from the stack. Store register LR SP. Load register LR SP. So the problem we're going to run into, I think, is how SP is configured. SP points to something, but it's kind of pointing to the wrong place because the stack pointer always points to the previous thing that would might have been stored on the stack. So if we do this, I think it's not going to work. I don't know, it does something, but I don't think it's going to be able to load it. It works. See, the problem is that we're using the stack here, but we're not using it correctly. You're supposed to be using it as a stack, which is a data structure, not just using it as a memory location to read and write from. So we have successfully run our program. We're just not doing it properly. We'll see how to use it properly soon. People are asking questions I'm going to answer soon when we talk about the stack. The stack, sneaky peek. So we've got this final register, the stack pointer, another special register. The value of SP, this is just by convention, is the address, an address in the SRAM region of the address space. And it's memory that you're going to use to get things done during your function. So if you're inside a function and you need to store some variables that are just local to that function, you'll store them on the stack. And we're calling it a stack. It's got this feature of being used as a data structure, as a stack. That is, when you call some function, it starts putting things on the stack, moves the stack pointer up, moves the stack pointer up, and then when you get to the end of that function, you drop the things off that you were using before. So you can always know where your stuff is inside a function because it's stored there on the stack. And if you run some function and it puts some stuff on, at the end of that function it should be dropping them back off again, so that your stack pointer is back in the same place. The question is, should we expect the stuff that a function pushes on the stack to be popped off at the end? Yes, we should. Or we should be keeping track of our stack, the stack value at the start of a function in order to use it to make relative loads from local variables, which is starting to get a bit mind-boggling, but we've got some diagrams in a minute. So each function sometimes sets up what's called a context within the stack, which will be some relative memory addresses on that data structure. We'll get to the stack later. We're going to talk first a little bit about being a good citizen as an assembly programmer, what a calling convention is, and this is really mostly related to inputs and outputs to our functions. So just keep all of these difficult stack questions in your head. We're certainly going to have a big stack discussion, but it takes a bit longer than we can go into just in 5 minutes. Calling conventions. So we answered this program. How does the program know where to come back to? LR. Can we have some scribble paper? We sort of know that that's the stack, but we're not quite sure how to use it yet. So these two questions are the ones we're going to look at now. How do we get information in, and how do we get information out? And all of these things are, you could call them unwritten rules, except that they're written down. So they're written rules. But they're not rules that are going to break your compiler, or your compiler's not going to tell you if you're doing them wrong. So they're rules just for you as a programmer. That's why we call them a convention. Someone asked, do we use this SP just to save the LR? No, we use SP and the stack to save everything we use when we're doing a function. All kinds of things go on the stack. You'll see about it later. You just have to trust me that we're going to get to that. So you might have seen this in some of the slides when we have a kind of mathsy representation of a function. Assume x is in R0, some kind of English language version, human readable version of telling us where the parameter is for our function. So it turns out that we have this kind of universally agreed upon plan for how to put the inputs and outputs of a function in registers, or in memory, in fact. Great question I'm going to answer later about stack and PC. this agreed upon plan for where to find inputs and leave outputs. So this plan does exist. This plan does exist. It's called the calling convention, and in fact, there's a PDF document and a website about the ARM. I think it's called the Procedure Calling Convention, Procedure Calling Standard, the PCS. So it's an agreement about how we're going to deal with the registers during a function call. And the reason we need this is because, like, I might have used a bunch of registers up here, MOV R1 6, MOV R6 12, MOV R7 1002. I've done some stuff, but +2 might also want to use MOV R7 for something else, 87. So hang on, is +2 allowed to use, is this function allowed to use R7? Is it allowed to use R0? What does it have to do? Are there any rules that I shouldn't be clobbering R7 when I run my function? Because if I want to get, add R7 1 and assume this equals 1003, if I'm making assumptions about R7 sticking around, my program is going to break because +2 has used R7 for something else. So there are rules to help us, or conventions to help us make sure we know how to deal with registers during our function calls, which is what we're going to talk about now. What happens between the label and the BXLR? What's allowed and what's not? So what does the CC specify? It lets us know where we want to look for parameter values, those are inputs to our functions, where we need to leave outputs for our functions, which registers we're allowed to mess with, which ones to leave alone, and in fact, rather than leave alone, really we mean which ones we need to save and put back when we're done. So let's have a look. Here's a function. Here's a function, int do all the things. It's a sort of Java-y C function. In brackets, int how many things. Then we do none of the things and return 0. So which calling convention does this function use? Do we know? It doesn't seem like it's going to do anything. But is it working correctly? I'm not sure. It returns a number. It doesn't really, we're not guaranteeing, I mean, it says it's doing some things, it's doing no things, but the calling convention is not actually about whether the function works or not. Whoops, works. That's not part of the calling convention. So even though this function is broken, it might still work with a calling convention. So in some sense, the idea of the calling convention is that it's your responsibility to do things according to that way. But there are other options. You can make up your own calling convention and just use that. You could just ignore calling conventions entirely and hope that your program works. But it's typical that people tend to use the ARM standard call convention when they're using an ARM processor. It's just seems to be relatively polite to do things that way, so that when someone else is reading your code, they've got a reasonable expectation of what should be happening. And in fact, you'll come across this in your lab this week. Oops. In your lab this week, not to jump ahead, but you'll do a few things with programs, but you'll also load in a big stack of code written by one of the tutors in a file called audio.s. And then during your code, you'll use a few functions that are defined in audio.s. And you can bet that the author of this code, which is Benjamin Gray, has used the calling convention to make sure that give you some assurance about which registers will be left correctly when you're not, will be left back the way they were when you were using your function, and which won't be. So here's a calling convention example. Do these two things both give us the right answer? What's the difference? So they're both the +1 function. This one uses R0. This one uses R5. And it's using R2 as the input. So that's the input and R5 is the output. Add R2 plus 1. This one's doing R0 plus 1 and R0 is the output. Now, if you look at this one and you're a bit confused, thinking R5 and R2, those are weird choices. I would agree, those are weird choices. And in fact, they're weird just because they seem very arbitrary. Normally you would like choose the lowest valued register to do something simple, like moving a number in and out of a function. And in fact, this is the way that the ARM calling convention would suggest that you do this procedure. Calling convention. R0 can be used as an input and R0 can also be used as the standard output. If you were using a bunch of functions, you got a library of functions from someone else and they said, oh, always use R2 as the input and R5 as the output, I think you'd think that it was a little bit weird. So here's the ARM architecture procedure call standard. It's a whole deal. I think you can, image, no, link. It's a whole document. You can go and read all, it's not that long, 33 pages. Pretty useful. But here's the important stuff about what registers should be doing with functions. These four registers, R0 to R3, they're going to be for parameters. So that's the inputs. They're also scratch. That means that the function can do whatever they want with them. Function can overwrite. R0 and R1 are also called the result registers, so the outputs. So we can, just with those two registers, we can get a simple output, which might be one number with 64 bits of precision or 8 bytes of important information, or any way we need it. But our R0 and R1 are the main result registers you'll use for simple functions. We've got these other registers, R4 to R11, and these ones are all called call save registers. So these ones mean functions need to put them back. Function puts back. So if a function wants to use R4 to R11, it's free to, but it needs to store that data somewhere safe and put it back the way that it was before returning, before the BXLR. Then we've got our last four registers, which are special registers. On our Cortex M4, really only R13 to R15 are special. We don't really have this one. Nah, don't need that one. SPLR PC. What are these scratch register things? I guess I just told you this, but it's on each slide just so you can remember it. These are registers that the caller can freely use and not worry about messing anything up. So the callee, actually, not the caller. Callee. Callee is the function being called. One time a student, or a couple of years back, a student cornered me after a lecture, maybe the week 1 lecture, and said, I don't understand caller, callee. And at some point I just said, look, just wait until we get to this lecture and I'll explain it. But the caller is the code calling the function. And the callee is the function being called. They're both bits of code, right? not particularly different except that one is a function and one is the code calling that function. So R0 and R3, the callee can use them for whatever, not worry about mixing them up. And they're often also called caller save, because if the caller, the code calling the function, wants to keep them, they need to be saved somewhere before branching to the functions. So if you are branching to a function, you have no guarantee that R0 to R3 will be the same as they were when they get back. This used to happen in an assignment in previous years in this course, that people would do a lot of important stuff in R0. Comment, important, don't erase. But then they would like branch and link to some library function and then come back. And then they'd be putting on Piazza, my code's broken, it doesn't work. Well, where was your important number stored? R0. Did you branch to a function? Yes. All right, well, is it the same number as when you come back out of the function as when you went in? Oh, yeah, so there you go. Save things before you put them into a function. So I haven't told you really that much about saving things, but we can talk about different ways of getting data in or out. So far, we've just been getting data in and out by putting it into a register and expecting it to be in a register on the way out. So if you recall back to some of your first year computing, you might have talked about this concept of passing by value and passing by reference. So some functions are sending a value to a function for it to edit and then give you that value back. And sometimes you're sending a reference, which is really a memory location, giving that to a function, and then that location in memory is edited. And when you return, you're not really returning any value. You're just returning to the previous code, which can then keep using that memory location. So in this one's passed by value, there's a number going in. R0 is a real, that's the value we want to change. Value to be used. And the output is in R0 as well. Passed by reference, we'd have to have some agreement about where in memory something has been stored, but we could send in a memory location, or we could assume that the function knows to find something in a particular memory location. In this one, it's finding the value in SP. So the function is getting the value from memory, in memory somewhere. It's getting it into the function and then it's storing it back again at the end. Two different ways of dealing with inputs and outputs to functions. What's the difference here? Why would we be need to use different ways of getting data in and out of a function? Good comments here. Someone's asked, can we do anything with R12? I think so. Mov R12, 102. If it stops me doing it, we can do anything. It doesn't stop me doing it, we can do anything we want. I got some problem with my code. What have I done wrong? No, it's R12 is not another scratch register. It's we'll go to the exact procedure call standard. Where is the registers? Yeah, it's often called a scratch register. I think it is defined that way. Yeah. Wrong comment character. Ah. Always get stuck by comment characters. And VS Code is not giving me any useful information that I've done the wrong thing. Yep, R12 is you're allowed to use that as a scratch register. You may use R12 as a scratch register. Pass by reference, in this case, down here, the caller and callee are looking at the same data. In this instance, caller can overwrite it gets a copy really, because even though they both might be, this might be some location in memory like OX2, OX2. In this case, we might be getting some data, want to run a function on it. We've retrieved the data from memory, stored in R0. Then we get back a new number in R0, and then we get to choose what to do with it. Our original value, which might be in memory, it might be somewhere else, hasn't been touched so far. So it's really, this one is getting a copy. The top one is getting a copy, although, you know, what copy means in assembly is exactly what you want it to mean. You get to make a lot of decisions about how these things are interpreted. In this one, we're editing the original. We get given a copy and then we send back a new number. In this one, we're editing the original in the code. Pass by value versus pass by reference. Pass by value makes a copy. R0, we're giving it a number in R0. That means we expect someone to mess it up in our function, change it. And if there was something in R0 we wanted to keep, we're keeping that somewhere else. Pass by reference, we're giving the function access to the same original data which we had in the starting point. These are both useful in different scenarios. There are pros and cons to both. In general, most of your data will have to live in memory because registers are not big enough. You've only got, as we said, a bunch of bytes, a couple of tens of bytes, not enough memory even for a significantly long string, right? You can hardly even fit a sentence into registers. It's only for a little bit of data to work on at a time. Folks are putting memes in my chat. The stack, we finally get to the stack. I'm going to keep going for a while because I think we're going fine, and I want to get through as much as possible so that on Thursday we can do a few fun demos. But maybe we'll get to another fun demo today. So, what have we answered so far? We know how we get back from our adventure. We know how to get parameters into our adventure, either registers or memory. We know how to get information out of our adventure in those particular callee scratch registers. Arguments at scratch register, argument result scratch register. Variable registers, that means that the function has to store them. Platform register, don't worry about that, it's just a variable register. Have a look at this document. It's actually kind of interesting and gives you some hints about how to actually write real production assembly, as much as that's a thing. Then finally, last question, can we have some scribble paper during our function? What else can of course we've got our scratch registers, but what about the other registers? How are we going to use those? What if we want some other local variables? How are we going to do that? You might have been used to coding in a high-level way like this. You have a function called doStuff with A and B, and then you just make a bunch of extra registers, a bunch of extra variables, I should say, bunch of extra local variables. Let C equals A plus B, let D equals A minus B, let E equals A times B. You could go on, have as many local variables as you want. But how are we going to do these in our functions where we don't want to mess up the registers that are already there, and we might want to have more local variables than we have registers? There's lots of issues here which we haven't dealt with yet. We could put C, D, and E in more registers, right? But that seems like it's a limited solution. What about more complicated variables like a dictionary? We don't have dictionaries yet in assembly. And what about an array with 1,000 items? We don't have 1,000 registers to store all those items. So there must be some way to store things that are bigger. Not enough registers for this stuff. So now we're back to the stack pointer and how the stack works. So the stack pointer is a memory address, and this is going to be used by functions for various purposes. It's a very multi-use thing, used for many things. It's going to be used for saving values in registers which would otherwise be overwritten. That is, LR is an example of something we need to save which might be overwritten. We're going to use it for, sometimes use it for passing parameters or return values. And sometimes we're going to use it for our local variables, our scribble paper. And it's called the stack pointer because that bit of memory that it points to is going to be used like a stack data structure. A last in, first out. First in, last out data structure, I mean. Now, in this regard, we have to be careful about confusing the stack in memory to a stack data structure in a higher level programming language. Although both of these things have the same name and they have a similar way of working, the stack in memory is very simple. In fact, there's nothing to it. It's just memory with a pointer. There's no protection against running off the end, making it too big. There's no protection against making it too small and your stack pointer running off the sort of backwards edge of the stack. It's memory and a pointer, and then we have a convention about the way we use it, which is to use it as a first in, last out stack. First in, last out means that you can consider this to be, think of it as memory with spots. We could store a number called A there, and then the next thing we store is B, next thing we store is C, and our stack pointer would be pointing up to the next spare space. And then we could also start to get things out. Get out C, get out B, get out A. We always have to go up and down in that way. The stack only works if you follow the rules. So it's not defined like in a high level programming language. Your programming language helps you not mess up your stack data structure, but the things don't help you to not mess it up in assembly. You have to make sure that your use of it is valid and make sure it doesn't get messed up. It's not too hard, you just have to follow the rules. So how does the stack get set up originally? If we just have a look in the starting file, starter, where's our stack? Letter SP. So we're putting a value in SP, which is defined by this number underscore stack end. Where's that defined? In the linker file, underscore stack end. It's defined to be the very end of RAM. So it's at the very top of our memory, which seems weird if we're going to use it, right? We need our stack to grow. Well, actually, the stack in this system, within our microbit, grows downwards, not upwards, which is a bit of a mind-bending concept, but it's useful that way. I'll tell you why in a minute. So our stack pointer in memory starts at this location right at the top of memory. it's handy that it grows down because we might have other stuff at the bottom of memory growing up. So we're using memory at the bottom for stuff, and then our stack pointer can grow down, and hopefully these two things never meet. And if they do meet, we're in big trouble. And our program is going to have some bad problems. So we deal with that later, the potential for the stack pointer and our other memory to meet. We'll just put that off for another week to deal with that, but it doesn't tend to happen, so we're not in so much problem, not in so much danger right now. The value of SP is just a pointer to a memory address is going to change as your program runs. So the SP can either point to the last address that was used, that's called a full stack configuration, or the first unused address, which is the empty stack configuration. Now, usually you don't really care about what the absolute address of SP was. You're not usually looking at it and remembering it or worrying about it. Primarily, you're using offsets to or from the SP address and not worrying too much. So a stack can grow up, and that would be called ascending, or it can grow down, and that would be a descending stack. And on the microbit, the convention is to use a full descending stack starting at the highest address in the memory space, which points to actual RAM. The highest address in the memory space pointing to actual RAM. There's a link to one of our address space slides. I wonder if that'll work. No, it doesn't. Whoops. Memory address space. Remember this thing? So our stack, not all of this whole region of SRAM is going to be actual RAM. It might stop here, right, somewhere, and our stack would start there and then grow this way, downwards. I think I've just lost my place in the previous, phew, still there. Stack instructions. So we can use stack SP just like any other register containing a memory address. But as we just learned, the stack pointer usually points to the last full used spot in that stack memory. So if we've got stack memory coming down like this, maybe it's, I'll keep going, it's this has been used, this has been used, this has been used, this has been used. The stack pointer points to there. So if we want to store something else on the stack, we don't want to put it in the place we've already used. We should be putting it in the next one, which is SP-4. So you can see I've got within this bit of code, which is, it's not a function, it's just a bit of code. We've got a number in R2, OXFE. We're going to store that number on the stack in the first free spot, which is going to be SP, -4. That's this empty spot. And then we're going to change the stack pointer to point to that spot we just filled. Then we do some stuff that might use the number, might not. And then we pop the value from the top of the stack back into R3, from the bottom of the stack, I guess. So this stores this into this new data. That's going to be OXFE. I think my head's in the way of that, so I'll try to get out of the way. Then SP is now defined to be this. Then we load this value into R3. And then we move SP back there. So as you run your program, as you use the stack, you always need to move the stack pointer so that it's pointing to the last used spot, full stack. So here's an illustrated push. Before the push, our stack pointer points to this used spot. I'll draw that, that's been used. Used. And we've got OXFE in R2. Then we want to push something on the stack. We copy OXFE into this location and we move the stack pointer down by 4 bytes, one word. Now we've got OXFE in the stack in that location. Stack pointer is pointing to the start of that word of memory. The questions have dried up. It must be everyone really focused on this. Oh no, sorry. Moving my head in the wrong place. Well, at least it's not in the way on this slide. Here's our pop going backwards. Stack pointer is here. The first thing we do is move, we popped into R3 there and moved our stack pointer upwards to the next spot, which was already filled in by something else. We don't know what that is. Where's the base of our stack? We don't know. Are we going to use too much stack memory? We don't know. In both cases, we don't know and don't care. So we're not going to worry about base of stack. How much memory? I'll get back to, someone's asked a really good question. How much memory available? Don't worry. I guess at this point we could use the Australianism, she'll be right, mate. She'll be right, comma, mate. So just try not to worry and love the stack. The sub. The sub is going to move the stack pointer. So each slot on the stack is 4 bytes. Each stack slot is 4 bytes, or more correctly, if we put something which takes 4 bytes onto the stack, we then have to move the stack pointer down to the point to the base of that area. Someone said, maybe instead of using the sub, could I just offset more or less when needed when loading and storing? Yeah, you could, but that's not the rules of how the stack works. Whenever you store to the stack, you must always move the stack pointer. Yep, you fill the stack. Someone asked if I fill the stack from the top. Absolutely, we do. Let's type it in. I'm not even going to use my functions now. I'm just going to use the stack. Oh yeah, we'll mov something into R3, I suppose. I'll do the example I had there, OXFE. And I'm going to store that on the stack. Sub moves towards the head of the stack. The head. Sub moves down in memory and add moves up in memory. The base of the stack is up. The latest thing in the stack is down. Oops, SP4. Letter. Okay, let's keep track of our stack pointer here. I feel like the stack pointer is not set up correctly because it let me store in it before, which should be out of range. But I'll check my linker file later. So I'm going to move this interesting value OXFE into R2. Then I'm going to store it on the stack, minus 4. Then I'm going to change my stack pointer by 4. Got a new stack pointer now. Now I'm going to reload that information back into R3. There it is. And I'm going to add back to my stack pointer, taking it back to where it was before. So this whole operation here is called a push to stack. And this would be called pop from stack, or just push and pop. Can we run this using the memory viewer? Good idea. But I'm gonna have to remember how to, what's a good number for me to start from? Calculator. I need one of those. There's some old school programmers calculators that used to be able to let you do arithmetic in hex. 1 EF01. Start again. View memory. OX2001 EF01. There's my memory here. This is stacking up to be a very interesting lecture. Dun, 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 dun. Here we do our, run my memory again. Okay, I hope this works. It's a lot of stuff here to be watching. I'm trying to make room. Move that aside a little bit. I just really need to see the SP. My poor little GPU is not happy with all the stuff that's being asked of it today. MOV R2, okay, FE is an R2 so far. We're going to store that on the stack, I hope. Where did it go? OX2001. It's covering the memory viewer. Oh man, I changed my head for a different lecture. Where's my head? Be very small. Bye. Bye guys. Okay, small head. (2001F) 201 EFFC. Oh, there it is. We found it. I'll run that again. It should be at the very... I hope I'm not covering it up now. Well, it was already in the memory viewer, but I'll put some more things on the stack in a minute. Never mind, there it is. FE00000. So at this point, the stack location is OX2001 EFFC. There's C. That's where my stack pointer is going. I'll just check that my head's not on the way. No, it's fine. Cool. And then when I pop from the stack, letter R3SP, add that. And the stack location is now OX2001F000. Somewhere else there. So let's do some more pushes. MOV. We'll just put some more stuff in R2, OXAA. Push that. Okay. putting a few things in the stack. I think maybe I need to start my memory viewer again. I'm not quite sure. I'm never quite sure about my memory viewers in in assembly. Well, it's still got that thing there from before. Oh well. It's stuck there in RAM. We should be able to override it this time, I hope. Move the SP. We're moving the stack pointer, stored that FE there, move the stack pointer to FF 2001 EFFC. 2001 EFFC, that's the last placed bit of memory. Then we move AA into R2, which will store that in memory. Ah, it works. It has stored it in the previous word, and then we relocate the stack pointer, and then we move R2, move OXEE into R2, good, and then we store that in memory. It works. We're doing it. 201 EFF4, EE000. So each of my numbers I've stored on the stack are going here in this procedure, and we keep going backwards through memory. And then we're going to pop something from the stack. What was the last thing I put on the stack? It was whatever SP is pointing to. SP is pointing to 2001 EFF4, 2001 EFF4, which is going to be OXEE. What if I want to get something from the stack which was further back on the stack? We can do that. It's allowed. SP8. So we're going to, instead of getting, we're not going to pop, we're just going to retrieve from the stack something into R3. Relative load from stack. So if we're not popping is sort of saying, I don't care about this data anymore, I don't want to store it, because we're moving the stack pointer back. That data is going to get overwritten. But we can access data we previously stored on the stack just by doing a relative load. So what data am I going to get out? And this is a question for you, using your brain. What data am I going to get out if I have run this line of code after these lines of code? There's probably some good questions here. What am I going to get out? This cup of coffee is very cold now. OXAA. Am I? So the stack pointer, SP, is pointing to 2001 EFF4. 2001 EFF4. Stack pointer is pointing there. So I'm going to load the word starting at that bit plus 8. 1, 2, 3, 4, 5, 6, 7, 8. It's FE. I think I've been watching too much Emma Wiggle with my kid, and now I've been giving COMP2300 lessons like FE. What do I find in memory? It's FE. How amazing. I should do more of this. Maybe I could turn COMP2300 into a kid show for preschool kids, for toddlers. Yeah, I've had a lot of devious exam questions. Before we did online exams, a really devious exam question would be to do a bunch of stores to the stack and then do a relative load from the stack and ask you students what number I've just loaded, and it would basically test your understanding of memory and test whether you know that the stack pointer is pointing to the last filled thing, or who knows where it's pointing to. I'm really pleased you folks are following along after the best part of 2 hours. Do you see how useful this could be, right? If we know if we can just always be storing things on and off the stack, we can have a lot of cases where we don't have to store special labels for memory anymore. We can push something on the stack, know where it is relative to our current position, get it back later, put something else on the stack, push, pop, do all of these things all the time. Now, let's just look at my slides. I don't want to blow your mind too much, but this push to stack operation, this is so useful and so important that we in fact have a one-liner to do it. Push R2. This line of code and this line of code do the same thing. Someone says we should use this for functions only, right? No, you can use the stack all the time. I mean, everything is a function. In the main label that you run is the start of a function. So whenever you're typing assembly code into your microbit, it's always in a function. It's in a function of something, someone's function. If you want to write code that's not in a function, you have to go into the startup file and start editing code from starting with the reset handler, not starting at main. So push R2 is so important that we have a shortcut for these locations, these instructions. And in fact, if I go down to my my loads and stores, it's not written here. There's no push on this page. Tell me, where's push? The tutor's made this for me. I'm going to complain. There's got to be someone I can complain to. Someone's just asked, what do I mean you can use it for anything? I mean, even if you're not in a function, you should use the stack for storing stuff. If it's not constant data, if it's a local variable that you want to save for later, store it on the stack and then get it back later. That's what it's there for. It's there to be used. Typically, I mean, I'm running out of time, but we did this push pop. Let's see what happens. Like if you write a function like this in C, the first thing the compiler is going to do is say, go to stack. This one goes on the stack. This one goes on the stack. Straight to the stack. Chuck everything on the stack. It's putting as much stuff on the stack as possible and then freeing up those registers for use in the actual function body. If you're not doing any, like, we'll look at this later in how compilers actually compile some code and what assembly might come out, but typically when you write a function and then compile it, the compiler just throws everything away that you're not actually using. So to do a kind of toy function, we have to turn all of the optimizations off. But regular functions store a whole lot of data on the stack. All of your local variables go on the stack. Where are we up to? Missing values in the diagrams aren't empty, just unknown. In our case, we knew what all of the information was, and we know that we're at the base of the stack here, but you know, we're not sure what all of these numbers are. We have to assume that they're things we can write over. They're uninitialized data. Offset load and store with write back. Oh no, there's a pop instruction, sorry. I just said there was push. No. This is, so we can just do the same thing. I'll run the program, here we go. Push R2, it's in brackets. Push R2. And do a relative load, and then we pop. I'll pop into R4 instead. So remember, this relative load doesn't use the, it's not changing the SP because it's just a load. We're not deleting that memory. By deleting, all we're doing is like moving our pointer away from it, so we're not pointing to it anymore. which means it's going to get written over the next time we push something. It's pretty much the same as being deleted, isn't it? We're just ignoring it. Mov R2. Oh, well, I got to change these numbers because they don't get changed in between loading my program. Probably if I unplugged my microbit and replugged it, it would get deleted. But I don't want to do that. Okay, Mov R2. It's weird. Push R2. There it is. AAOOO. Okay. Mov R2 BB. Push that. There we go. There it is. Mov R2 CC. Push that. There it is. We're going to just get something back 2 steps before. So our stack pointer is now here. 1, 2, 3, 4, 5, 6, 7, 8. I counted wrong. 1, 2, 3, 4, 5, 6, 7, 8. It's going to grab this number into R3, and it did. And then we pop whatever was the most recent thing from the stack, which is CC, into R4, and it did, just as we said. So push and pop. There's also other ways of doing this just with store and letter. You can use this exclamation point to indicate that you want to change the value of your index register, your memory address register, before doing the store or the load. So you can store something R0 in the memory address at R1 plus 4. But the first thing that you do is add 4 to R1. So at the end of this, R1 will equal R1 plus 4. This happens before we do the store. This is the same thing, but after the load, after the load or store. So we're taking the memory address, the comma outside the memory address, there's no exclamation point, and then we have -8. So it's going to load whatever is in R1 into R0, and then after that, we're going to change the memory address. So push is really this one. Push is equal to store whatever rn, comma, sp4, or -4, I mean. Pre-offset, because we're moving the stack pointer by 4, storing to that location. And pop is post-offset. That would be letter rn, whatever register we want, sp, comma 4. So it's loading whatever is the latest, the top of the stack, sp is pointing to, then changing sp to the previous location. Offset, load, and store with write back. Don't forget these instructions either. Some of the instructions which get to be a little bit more confusing and advanced are these special memory reading and writing instructions. Post-offset, pre-offset, push and pop. They can feel a little bit more complicated, but they're very useful in writing more complicated algorithms. And that's where I'm going to stop. We can talk about this stuff next time on Thursday morning. So we'll just do a tour of where we're going. Stack pointer examples, push, pop, the push and pop instructions. You can actually do more push and pop a whole lot of registers at once, which is really convenient. And then some details of that. We'll talk about this stuff next time and get to some more details about the rules for using the stack within functions, which should be really fun. So thank you so much for your great questions and thoughts this time. Do not forget to write your design proposal before your lab so that your tutor can access it and that you get a great mark for that. Remember about the design proposal, the mark is less important than the feedback you get about your assignment idea. because it could lead you down the right path towards doing a much better assignment than you might if you didn't ever get any feedback about your idea before starting. So the feedback part, the discussion with your tutor, is super important. I'll catch you folks on Thursday morning. Until then, have a great week.